Good morning, everyone, and welcome back. Last time we experienced something rare and beautiful in fluid mechanics. We took a simple force balance, combined it with Newton's law of viscosity, and derived an exact, elegant solution for laminar flow in a pipe. We got the parabolic velocity profile, Poiseuille's law with its d raised to the power 4 dependence, and the clean, simple friction factor as F is equal to 64 over Reynolds number. It was neat, it was tidy, it was perfect. But here is the honest truth. Since a turbulent pipe flow is actually more likely to occur than laminar flow in practical situations, it is necessary to obtain similar information for the turbulent pipe flows. Most of the flows you will encounter in the real world, such as water gushing from a fire hose, air rushing through ventilation ducts, oil pumping through a pipeline, are all turbulent. And unfortunately, as the textbook puts it, that the turbulent flow is a very complex process. It is, and I quote, that the least understood area of uh, the fluid mechanics. So today we cross the great divide. We leave the orderly, predictable world of laminar flow and enter the chaotic, random, and fascinating world of fully developed turbulent flow. Our goal is to understand its characteristics, its structure, and how it differs from the laminar flow we already know. So, moving towards the transition from order to chaos. Let us start by talking about how we get from laminar to turbulent flow. So remember Osborne Reynolds and his dye experiment from our very first lecture. So that experiment did not just identify the laminar and turbulent flow, it showed us the transition between them. Now imagine a long pipe, initially with no flow. We slowly open a valve. The Reynolds number increases from 0. As it passes through the pipe, the flow is not instantly turbulent. There is a process, as illustrated beautifully in this figure. At first, it's laminar, smooth, and orderly. As the Reynolds number passes about 2100, the flow enters a transitional phase. You start to see intermittent bursts of irregularity, spots of turbulence appears, and then this disappear. The flow flickers between order and chaos. It's unpredictable. And finally, as the Reynolds number exceeds about 4000, the flow becomes fully turbulent. The entire pipe is filled with that chaotic random motion. So, this randomness is the defining feature of turbulence. Now, look at this figure. It shows a trace of velocity at a single point in the turbulent flow. It's jagged, spiky, and seemingly unpredictable. It never settles down to a constant value that like it would in laminar flow. So how do we even begin to analyze something so random? The answer is statistical. We decompose the instantaneous velocity u into two parts. A time averaged mean value, which we denote with an overbar u bar, and a fluctuating part, which is hereby represented as u superscript bar, which represents the random excursions from the mean, which is hereby also represented by the equation as u equals to u bar plus u superscript bar. The mean value u upper bar is what we would measure with a slow responding instrument. It's the average behavior. The fluctuations U superscript bar are what make turbulence so effective at the mixing. And while the average of the fluctuations themselves is zero, so U superscript bar and upper bar must be equal to zero. The average of the square of the fluctuations is positive. So this gives us a way to quantify the strength of the turbulence, which is also called as the turbulence intensity. Now, the heart of the matter is the turbulent shear stress. Now, here is where we move from description to physics. In laminar flow, the shear stress came from a simple molecular scale process, molecules darting randomly across streamlines, carrying momentum with them. So this gave us tau is equal to mu du by dy equation. In turbulent flow, the molecular process is still there, but it's completely dwarfed by a new, much more powerful mechanism. To understand it, look at this particular figure. The part A shows laminar molecular flow, a molecular view, but the part B shows a turbulent view. Now think of the turbulent flow not as a collection of molecules but as a seething mass of random three-dimensional eddies. These are chunks of fluid ranging from tiny to quite large that tumble and swirl as they are carried along. As these eddies randomly move across the pipe, they transport mass, momentum, and energy in a way that molecules simply cannot. Imagine a plane across the pipe, an eddy moving upwards, carrying with it the lower x momentum from its point of origin, and eddy moving downwards carries higher x momentum from nearer the center line. This macroscopic momentum exchange creates an enormous apparent shear stress. This is the turbulent shear stress, and it's given by a term called the Reynolds stress, hereby written by the term minus rho u, u bar, v bar, and a whole bar. So the total shear stress is the turbulent flow is the sum of the laminar and turbulent parts as given by this particular equation. Tau is equal to mu du by dy minus rho u bar v bar whole bar must be equal to tau of the laminar part plus tau of the turbulent part. So this is a profound statement. The shear stress is no longer just a fluid property times a velocity gradient. It now depends upon the correlation between the random fluctuations themselves, which is hereby represented as u bar, v bar, and average of u bar, v bar. And determining this term is the central change of the challenge of the turbulence. So one way to think about it is to define an eddy viscosity eta such that the turbulence tau, tau turbulence must be equal to eta du bar by dy. This looks just like the laminar formula, but there is a catch. The laminar viscosity mu is a property of the fluid. You can look it up in the table. The eddy viscosity eta is not a fluid property. It's a property of the flow. It varies from point to point in the flow and depends on the level of turbulence. It's different for a flow fast than a slow flow, than a slow flow. So while the concept is very useful, it does not give us an easy answer. So if we can't solve for turbulent flow exactly, what can we do? We can observe it, and observations combined with brilliant dimensional dimensional analysis have revealed a distinct layered structure. So now look at this figure. We can divide the flow into three regions based on distance from the wall. The first one is the viscous sublayer. The second one is the outer layer, and the third one is the overlap layer. Now describing uh, all of these three one by one. The viscous sublayer, this is the region immediately adjacent to the wall. It is incredibly thin. In this layer, the turbulent fluctuations are damped out by the presence of the wall. The flow is almost laminar in character. Here, the laminar shear stress, tau laminar, is dominant, and the velocity profile is linear and is given by this particular equation as represented, where u steric is the velocity scale and is called as a friction velocity. Now the second one is the outer layer. This is the bulk of the flow away from the wall. Here, the turbulent eddies dominate, and the Reynolds stress, which is represented as tau turbulent, is orders of magnitude larger than the laminar stress. The flow is well mixed and chaotic in this layer. Now, the third is the overlap layer. This is the transition region between the viscous sublayer and the outer layer. Both types of stress are important here remarkably by matching the behavior of the inner and outer regions. In this overlap layer, we can derive a universal velocity profile called the law of the wall and or the logarithmic profile, which is given by this equation as u bar over u steric equals to 1 over k natural logarithm of y u steric divided by nu plus b. Now here k, which I am speaking as k, is the kappa, and b are constants determined from the experiments. This logarithmic equation, as shown in this figure, fits experimental data incredibly well over a wide range of Reynolds number. Now, this layered structure has a huge practical implication. The viscous sublayer is a gatekeeper. Its thickness is on the order of sigma b equals to 5 nu divided by u steric. For a typical water pipe, this layer might be only 0.002 inches thick. That's thinner than a human hair. Now, because this layer is so thin, any roughness on the pipe wall eta that produces that protrudes through this sublayer will completely change the flow. As shown in this figure, if the roughness elements are buried within the sublayer, the pipe behaves as if it is hydraulically smooth. But if they poke through, they generate their own turbulence and increase the wall shear stress and pressure drop dramatically. This is why pipe roughness is a critical parameter in turbulent flow, where it had no effect in laminar flow. So, for quick practical calculations, engineers often use a simpler approximation, that is the power law velocity profile as represented over here. So, the exponent En is a function of Reynolds number as shown in this particular figure. For many flows, N is around 7, giving the famous 1 by 7th power law. This profile is not as accurate near the wall, but it's much easier to integrate to find things like the average velocity. Now, let us bring all these abstract concepts down to earth by working through the numbers in the example from the textbook. This is a fantastic illustration of the ideas we have just discussed. We have water at 20 degrees centigrade flowing in a horizontal zero point 0.1 meter diameter pipe. The flow rate is 0.04 meter cube per second, and the measured pressure gradient is 2.59 kilopascal per meter. Now, in the part A, it asked that to determine the approximate thickness of the viscous sublayer. First, we need the wall shear stress tau W. Even though the flow is very turbulent, the force balancing we derived last time as delta P is equal to 4L tau W divided by D is still valid. It comes from the basic mechanics independent of the flow type. So we first calculate the tau W, then we calculate the friction velocity U star as under root of tau W divided by rho. And from the figure, we know that the viscous sublayer extends to about y plus equals to 5. So sigma comes out, the thickness comes out to be 0.02 millimeter. So that is incredibly thin. This is why even small scratches or rust bumps on a pipe wall can have a huge impact on the flow resistance. Now, part C of it asks to determine the ratio of the turbulent to laminar shear stress at R is equal to 0.025 meter midway to the wall. So from our linear stress distribution, the total shear stress at this point comes out to be 32.4 Newton meter, and we can estimate the laminar component also by using the power law velocity profile at to get the velocity gradient. So the calculation yields the tall laminar as 0.0266 Newton per meter square. So the total shear stress is the sum of the laminar and the turbulent parts, and we can write tau is equal to tau laminar part plus the part of the turbulent region, tau turbulent. So it comes out to be tau turbulent as 32 Newton per meter square. So what we have to find out in this particular example problem is the ratio of the turbulent to the laminar uh, tau. So tau turbulent divided by tau laminar comes out to be 1220, 1220. So at a point halfway to the wall, the turbulent shear stress is more than 1000 times larger than the laminar contribution. So this is overwhelming dominance of turbulence. The laminar part is practically negligible. This one number captures the entire reason why turbulent flow is so different, why it mixes so well, and why it creates so much more resistance. Now, coming towards the turbulence modeling and chaos, now you might be wondering that if we cannot solve for turbulence very exactly, and if the eddy viscosity is not a constant, how do engineers actually design the things? So this is where turbulence modeling comes in. Now we go back to the governing equations, which is the Navier-Stokes equations and the time average, and then we would be time averaging them. But as the text explains that the process introduced new unknowns, the Reynolds stresses, we now have more unknowns than the equations. This is the famous closure problem. To close the equations, we need models. The simplest are the algebraic models, like the mixing length model we mentioned earlier, which assumes Lm as a function of the distance from the wall. More complex models, like the K epsilon model, solve additional transport equations for turbulence quantities. This is the massive field of research, and it's what allows CFD, computational fluid dynamics, to make predictions of turbulent flows. And finally, it also touches on the cutting edge idea, chaos theory. Some researchers believe that the turbulence may be a manifestation of deterministic chaos. The Navier-Stokes equations are nonlinear. Chaos theory tells us that nonlinear systems can be exquisitely sensitive to initial conditions. A tiny change in how you start the flow could, at high Reynolds number, lead to a wildly different, seemingly random outcome. This is the fascinating and active area of research that may one day provide a deeper understanding of turbulence. Now, let us bring this all together. Today, we stepped into the chaotic world of turbulent flows. We saw that it is characterized by the randomness and fluctuations which we describe using mean and fluctuating components. We learned that the shear stress is dominated by the Reynolds stress, a macroscopic momentum transfer from the tumbling eddies, which is vastly larger than the laminar stress. We also discovered that the turbulent flow has a layered structure, a thin, linear viscous sublayer near the wall, a turbulent outer layer, and a logarithmic overlap layer connecting them. We saw through example that the turbulent shear stress can be over 1000 times greater than the laminar part, and that the viscous sublayer is incredibly thin, making the flow sensitive to pipe roughnesses. And we also acknowledged that while we cannot solve for turbulence exactly, we have models and a growing theoretical understanding to guide us. So this is a huge difference from laminar flow. Next time, we will take these concepts and use dimensional analysis to tie everything together. We will define the friction factor for turbulent flow, introduce the Modi chart, and learn how to calculate the major losses that dominate the real world piping systems. So, see you then.